Thank you. Okay, folks, so I'm conscious that we're having a bit of a late lunch, and I'm just before that late lunch. So I want to keep it fairly snappy with that in mind, okay? Talking to Malcolm, he suggested that I change my topic to talk about stress transfer, earthquakes and stress transfer, which is a fairly new and exciting area of research that tackles the problem I was talking to you before about, was earthquake forecasting. Okay, generally trying to get to grips with earthquakes, trying to understand them better, trying to reduce the death toll in earthquakes. And you remember I mentioned it a couple of times, wherever it was I talked to you last, in connection with, in particular, the North Anatolian fault. And as I remember, nobody drew a complete blank because, well, that's amazing. So anyway, I want to fill that blank with this this talk, okay? So, right, so for a long time, sort of anecdotally, it was noticed that an earthquake would occur on one fault, and then fairly soon afterwards, another fault, maybe within years or even less time than that, another earthquake would occur on a nearby fault. And so anecdotally, there was this idea that somehow earthquakes didn't operate in isolation, that an earthquake occurs and that changes things, and so promotes a subsequent earthquake nearby. And that was, as I said, a sort of anecdotal idea that was kicking around until a famous earthquake in Eastern California in 1992, the Landers earthquake. So I want to show you the sort of development from this anecdotal idea to, in particular, the example from Eastern California, the Landers earthquake. Also some other examples from California. I've also found one from Italy. And of course, I will mention about the North Anatolian fault, so that nobody's, in future, when somebody asks you what you know about the North Anatolian fault, you'll be able to say, yes, I was still awake at that point, and yes, I do remember that. Then also, there was this, or I'm seeking your help here on the so-called Eastern Mediterranean earthquake swarm, because it delves into, archaeological matters and obscure names of places I don't know. Yes.
Swarm or storm?
Storm. Did I say storm? Oh, sorry, storm.
Yeah.
Storm. Sorry, storm. Yeah. And of course, this does relate to the idea of seismic gaps that I talked about before, and the idea of earthquake forecasting I talked about before. Okay, so here is just a bit of context. This is Los Angeles here. So this is the Mojave Desert, defined by the San Andreas Fault and the Garlock Fault here. And there was this series of faults, these northwest, southeast striking faults. And this was the area in which this stress transfer was sort of nailed down. Okay? This is a famous photograph of this earthquake, the Landers earthquake I mentioned, with one of the very first. This was on the cover of Science magazine, and it shows beautifully the deformation fringes in this interferogram associated with displacement on this fault here, this 7.3 magnitude earthquake. So this goes back to a French naturalist, Coulomb, who quite reasonably related failure in rocks to the shear stress across the failure plane. what is driving that shearing. Pore pressure, we talked about pore pressure before in the context of landslides, so that's going to be opposing friction, isn't it? Normal stress, so stress at right angles to that failure plane, and frictional resistance, which of course is going to be opposed, as I said, by pore pressure. So putting all together those factors, you end up with a quantitative value for rock failure. Now, an earthquake, of course, changes the distribution of stress around the fault, as I'll show you in a moment, following the Coulomb model. It's important to note that these stress changes are quite small, really quite remarkably small, something on the order of an atmosphere or a couple of atmospheres, not very much. But it seems that if the failure of fault, if a fault is close to failure anyway, that small change in stress represents a straw that breaks the camel's back. Of course, we don't know how close to failure a fault might be, although you remember one of the things we talked about last time was earthquake readiness, fault readiness, which is a step towards addressing that question. Aftershocks and future earthquake main shocks tend to occur where stress rises, and so this is a fact. As I'll show you, however much you may be skeptical about stress transfer, there's no doubt that aftershocks cluster in areas of stress rise. So as I said, an earthquake's not operating independently, and there's a number of historical, more anecdotal arguments for that. So here's this Coulomb stress change that I talked about. So if we just look at this, this is the change of stress after an earthquake. In this case, a right lateral strike slip fault. You can see the ends of the fault represent areas of stress rise, just as you'd expect, because the rupture has come to an end. And the length of a fault, which has had accumulated elastic strain energy and that has been released, that's an area of stress drop. Okay, and that color scheme we're going to use just to sort of take you through a little sequence in this so-called Eastern California shear zone, part of this Landers earthquake set of faults that I already mentioned. So here's the area where those faults, Landers is somewhere down here, okay? And the proposal is that up here is something called the Walker Lane, which has been known about for a long time, an area of increased seismicity on the border of California and Nevada. And as a result of these earthquakes that I'm about to tell you, that Walker Lane has been linked to something now called the Eastern California shear zone. So when you put that together on a map, you end up with something like this. Okay? So here's the plate boundary at the moment, and you remember I talked about the big bend of the San Andreas here. So in terms of plate dynamics, that big bend is, as I said, it was a restraining bend, and is rather a sort of perturbation in the smooth plate boundary, idealized smooth plate boundary. And so the proposal is, just a proposal, is this Eastern California shear zone linking through to the Walker Lane and continues up to the Cascade Arc there, is an incipient new plate boundary. And I've made a note here, terrain tectonics. Those of you who are familiar with the concept of suspect terrains and exotic terrains, places like Rangalia, these are all, the whole of the Cordillera and Western Cordillera margin of North America is made up of these slices, these fault-bounded slices or terrains, which have been moved great distances, thousands of kilometers, and reassembled, particularly in Alaska. So it's like a sort of, almost like block, an ice pack ice, moving blocks of ice imagery. Maybe. Anyway, we can't go on to that in any detail, but of course, so there's the idea. It sort of straightens out the Big Bend. And so here's the sequence of earthquakes, okay? Of course, this is in hindsight. There's always that wonderful thing. So there's Landers, and here we've got the timeline starting before 1975. So the first thing that happens is a modest earthquake on this to-be future Eastern California shear zone, magnitude 5.2, Galway Lake earthquake. Nobody pays any attention. Then 4 years later, there's a slightly bigger earthquake on an adjacent fault. This was the Galway Lake earthquake, and you can see these are areas of, these lobes are areas of stress rise. These cool colours, blues, are areas of stress drop. And so in hindsight, you might think, well, the Galway Lake stress rise maybe feeds through to this Homestead Valley earthquake that happened 4 years later. Okay. And so that continues in 1986, after a 7-year gap. There's a magnitude 6 North Palm Springs event, and in 1992 the 6.1 Joshua Tree earthquake, and then the Landers event itself 6 years later. At this point, nobody is talking about stress transfer. Okay, these are just events that are lost in the mass of other earthquakes that occur in California. But what happened is 3 hours, 26 minutes later, after the Landers earthquake, there was this Big Bear earthquake. Big Bear is a ski resort in the San Bernardino Mountains. And you could see this is squarely in the area of stress rise. And it was that sequence, the Landers earthquake, and then immediately followed by the Big Bear earthquake 3 hours later, that really provided sufficient evidence for the community to be convinced about stress transfer. And further earthquakes, what's that? That's 7 years later, another big earthquake, the Hector Mine earthquake. And you can see the pattern of aftershocks, again, favouring areas of stress rise. I'll come back to that point. This is just a sort of oblique view. You get the picture, I hope, with the Hector Mine earthquake and the aftershocks. Okay, any questions on that? Okay. Good, so let's now, I sort of alluded to this briefly, but now let's just consider the Bay Area. Now, before that, Bay Area is noted, of course, for the San Francisco earthquake in 1906. But there are many faults in the Bay Area. There were 3 or 4 big faults that basically define the margins of the Bay Area. And before the 1906 event in that 75 years, which is pretty much California recorded history. If you know about the 1849 gold rush thing, that was when, so anything before then is basically Indian legend and stuff like that. There were some Spanish missions, but basically the historical record is very short. Anyway, most notably, before 1906, there were 14 of moment magnitude 6 or greater earthquakes around the Bay Area, including 2 fairly large events. And then after the 1906 event, there was only 1 earthquake. So there was quite a distinct change in the pattern of strain release, tectonic strain release, before and after the 1906 event. So again, if I might mention it, again, sort of throwing into a cocked hat the idea of recurrence intervals. Okay, so just a little illustration of that. So these are the earthquakes before 1906, and then only 1 earthquake on the Calaveras Fault here after 1906. What's going on? So here's the faults that I already mentioned, and the 1906, by relieving elastic strain, accumulated elastic strain, right through the middle of the Bay Area, as it were, this was as it were, put the whole of the Bay Area in a zone of stress shadow. It relieved the accumulated elastic strain energy. Okay, this is using that same approach, stress transfer to produce earthquake forecasting. This just represents another example from what I was talking about yesterday, or whatever it was last week. Okay, so I hope that's moderately convincing, interesting. So now I'd like to provide another example in Central California. Okay? This is on the Coalinga blind thrust, one of a series of blind thrusts associated with the linear segment of San Andreas. And that had effects on the creeping segment of the fault, north of Parkfield, and also on this Parkfield prediction experiment that I mentioned. Parkfield, is Parkfield on the telly? No. Okay, all right. This was a place, but there was lots of earthquake predictions happening. Earthquake predictions, not forecast predictions, okay? People, scientists, reputable scientists saying, oh right, there's going to be magnitude so-and-so, something, earthquake in, I don't know, Long Beach or something like that, say. And of course they publicised that, and it got in the newspapers, and then there was no earthquake. And of course there was general panic, well, panic, but general alarm, and then there was no earthquake. And so basically that situation couldn't continue with this repeat, people trying to make a name for themselves scientifically by putting forward these predictions that didn't happen. And so a blue ribbon panel of specialists from academia, USGS, was set up to vet earthquake predictions. And of those earthquake predictions, that panel allowed through 1 prediction, and that was in this place, Parkfield. I'll show you in a second on the map, which seemed to be so straightforward. The linear segment of San Andreas had been repeated moderate earthquakes every sort of 20 odd years, and it seemed like that was a repeating pattern that could be reasonably anticipated to continue. And so the prediction was there'd be a magnitude 6 earthquake or something like that in 1989. And on that basis, the USGS and other partners instrumented Parkfield to the hilt. In fact, you can go to Parkfield now. Actually, it calls itself the earthquake capital of the world. I think it's one of these places, you know, the thing, welcome to Parkfield, population 18. You know, but it's a great place. And there was lots of instrumentation with the idea that it was going to capture the premonitory signals of an earthquake. That's what you want, isn't it? To have your black box, to know what the black box signal is going to be before an earthquake. Because always the black boxes go in after the earthquake. And so it's always too late. You want to know what the build-up to the earthquake looks like in terms of foreshocks or, you know, change in water levels, or radon gas, or various other factors. Anyway, so we'll talk about that. I might say that 1989 came and went, and there was no earthquake, and people sort of, I can't even remember, the actual earthquake, I think, took place in 2003 in the end, by which time people had either given up, retired, gone home, or something like that. And the cruel twist of the knife that Mother Nature gave, the final cruel twist, was that there was no premonitory signals. When the earthquake happened in 2003, it just happened. There was no nice pattern of after foreshocks or anything like that. But let me just go to stress. So even that you know, widely accepted prediction failed. Why did it fail? Okay, here we come to the stress transfer bit. So wait for it. So here are these are a series of en echelon plunging synclines associated with deformation on the San Andreas Fault. So here's the coalinga that's with that fold wrapping around the tip. So we're just in sort of central California here. Series of those things. I might just show. From our present point of view, of course, what happened, the Coalinga earthquake, which happened in 1983. Remember? So that was before the predicted 1989 timing of the Parkfield earthquake in the prediction. In 1983, that threw a stress drop, a stress shadow over Parkfield. And probably that explains why the prediction didn't work. If you look at these creep meter records, basically it shows an interruption, or even in one case a reversal in movement associated with the 1983 event. So here we've got steady movement in the creeping segment of the fault, which was interrupted, in one case slightly reversed temporarily by the 1983 event. So put another way, here's this was the last earthquake in Parkfield, 1966, accumulating elastic strain energy, renewed probability, same thing. You can see here the 1983 Coalinga earthquake caused a reversal, temporary reversal in that inexorable build-up of elastic strain energy. And it wasn't until 2003 that that, as it were, sort of recovered. But as I said, by that time, most people had sort of gone home. Okay, any questions on that? Earthquake prediction, Parkfield. Might check it on Google. Lots of stuff. Okay, the Northridge earthquake, again, just making this point, another blind thrust in the Bay Area this time, south of the Big Bend of San Andreas. Again, concentration of aftershocks in the stress rise areas compared with the stress drop areas. Okay, in Italy, as I promised, and basically what you have here is a sequence of earthquakes going from northwest to southeast. Got that right? Yes. And put another way, so there was a faulting event, and that loaded an adjacent segment, and so on. So a sequential over the period of something like a couple of months. This is a north. You try to tell me you haven't seen this figure. You're kidding. Come on. It's okay. I won't tell anybody. Been looking at this sort of geological things like this on. Okay. Right, North Anatolian Fault. Okay. Most famously, just goes south of Istanbul, and this is the very, very interesting sequence of earthquakes, particularly here, a big earthquake that took place in this part of the fault, okay, 1939, 42, 43, 51, 44 here, 51, 57, 67, and then this August 1999 Izmit earthquake here, which is the penultimate segment of the fault next to the Istanbul segment. And there was, that's over 10 years ago now, getting on for 20 years ago. At the time, there was a great deal of concern that, right, stress transfer, this means that Istanbul is, that segment, the Istanbul segment is loaded and likely to have another earthquake. But, of course, as we all know, that hasn't happened.
Sorry.
Yes?
Previously,
I'm sorry?
the previously is like at the right side of the earthquake of 1939.
Yes.
Yeah, there are some earthquakes, but the rupture length is very smaller.
Yes.
So
yes.
we can imagine that in the future will be an earthquake compared with the other ones.
Here.
Yeah.
Because the accumulated strain energy has been insufficiently relieved by these earthquakes.
So
yeah, that's what you mean?
Okay.
I agree.
Yeah, it's an area that is loading energy.
Yeah.
And then okay.
Yeah. It's so difficult, isn't it? Yeah. So we would. Yeah. You on the face of it, you would say yes. This, in terms of seismic gaps, and all the plate boundary keeping up, as it were. Yes, this represents a seismic gap that's lagging behind, and therefore more likely to be the site of a future earthquake. Yes. Yeah, good point. It's of course Mother Nature. Well, Mother Nature's perfect, of course, but she is reluctant to reveal secrets, as we all know. So it's not. Absolutely, that's our job. Yeah, we're trying. It's not machine perfect, but good. Okay. And yeah, this is another represent. I usually put this up to highlight this person here, Rachel Margaret, who was a student of mine some years ago now. And she, just as a sort of like an inspirational story, she just came into my room one day and said, "Oh, I want to, kind of do something big or special or something like that." Anyway, to cut a long story short, she ended up getting in touch with, getting in touch with the USGS in Menlo Park, that's there, California, on office and have had a 1-year paid internship with USGS in Menlo Park. And that was purely from her initiative, her going out and sending some emails and making contacts and not sitting back passively waiting for something to happen. That was her being proactive, and I've lost touch with her now, but that's what can happen if you, I know you're all proactive. But okay, so a couple of other final examples, then we can have lunch, well earned. This is on the subduction interface that ruptured in the 2000, of course, the Sumatra and tsunami. This event here took place only about 4 months later. So there's some debate about whether that's strictly stress transfer or more likely a very, very large aftershock. The Tohoku event, I already gave you that example. And finally, this Politz bloke, he works with this chap Ross Stein at USGS, where Rachel Margaret was, and they're at the sort of forefront of this effort. Basically, these earthquakes, later earthquakes in 2012, associated with the Sumatran subduction zone, are in this paper published in Nature, so I guess it was thoroughly reviewed. Their proposal is that that through stress transfer, that earthquake off Sumatra here triggered an earthquake, what was it, 2 hours later in the Aleutian Arc. So an antipodal stress transfer. And you may have known, you think, oh, that's impossible. But actually, here's, for example, this was on the news, etc. The redistribution of mass in the Earth as a result of the Tohoku earthquake cut short the day, the Earth days, by something like 2 millionths of a second. Not much, but it shows you the effect that is possible. Okay, so the Eastern seismic storm thing, storm not swarm, that we talked about. So yeah, this is where I kind of glaze over a bit, but there was a number of these Levant, I guess that's in sort of Israel or Middle East. Okay, Palestine. But in this period here, okay, and a number of cities, which you're, I'm sure, familiar with, collapsed. So I guess these were civilization, city-states or something. And the suggestion is, if you look at this map here, it's not too difficult to think, well, there's actually a lot of potential for stress transfer. Here's a North Anatolian fault we've been talking about, of course, which accommodates the westward movement of this Anatolian microplate, the East Anatolian fault. So this microplate is being expelled westwards and extending here in the Aegean Sea before subduction here of the Hellenic Arc. And as I say, a number of those, I don't know if anybody could throw in something at this point about those archaeological places. Yes, I thought not. Getting close to lunchtime. Okay, maybe over lunch. Okay, some criticism. Fine, last slide. Okay, so we can't. Yeah, this is modelled. These stress changes are modelled. Okay, using the Coulomb criteria, not measured. So that's one, and the Earth is modelled as uniform, being uniform. Obviously, that's a simplification. However, as I've tried to show you, there do seem to be good correlations between the modelling and the actual occurrence of the earthquakes, aftershocks in particular. And also might mention as again that the change in stress is very small. Just something like, you know, having your bicycle tyre almost flat versus adequately inflated. Not very small, but of course, if a fault is just about to fail, that sudden loading, because that's what it is, isn't it? It isn't gradual, it's a sudden loading, may represent that final straw. So again, we don't know, despite the fault readiness, how close to failure a fault might be. So it's difficult. Okay, final point there about the suddenness of it. Okay, I think I'll tail off gracefully there. And are there any questions, or is it too close to lunchtime to have any questions? I thought so.